How to trigger a high-speed camera. For the example of that slap, you know it was coming, so it's easy. But if it comes as a surprise like Will Smith's Beauty, to capture it in slow motion, it's really challenging. You cannot film the entire Oscar ceremony with a high-speed camera. You need a trigger. The parameter important with high-speed camera is the number of frames per second. For instance, at 20,000 frames per second, an image is captured every 50 microseconds. During this short lapse of time, you need to collect the information coming from each pixel. For each pixel of a CMOS camera, there is a sensor that will convert the photon to electron, and then the electron is converted to a voltage. Each pixel of a CMOS camera is equipped with its own circuit, and what takes time is reading the voltage. Therefore, one way to increase the frame rate is to decrease the number of pixels you read out. CMOS cameras offer that flexibility. Now that you better understand how works a camera, we can come back to our Will Smith slap. At 20,000 frames per second, assuming that we have a good camera to cover enough pixels at this rate, 2 seconds of video will give you 40,000 images. Without any trigger, if you don't want to miss the slap, you need to film 3.5 hours of ceremony, giving you 252 millions of images. That's a bunch of useless images. In this video, I will give you a practical example of how to trigger a camera. I want to capture the exact moment when the cork of a champagne bottle takes off. I cannot film forever because I don't want to generate millions of images, and I cannot push the cork with my fingers neither because they will be in the way. My unique solution is to wait that the cork pops by itself and trigger the high-speed camera. So I placed a laser in front of the cork to detect the popping event. In front of the laser, I place a photodiode sensible to photons. This photodiode will send a 5-volt TTL signal if it is illuminated with the laser. Then I define two times, T1 and T2, that are the amount of time saved before and after the moment when the trigger reaches the camera. The camera erases directly what was filmed before that time because we don't need these images anymore, because the cork is still inside the bottle. When suddenly the cork pops, 5-volt TTL signal is sent to the camera as a trigger. Only the time T1 before the trigger and the time T2 after the trigger have been saved. To align everything without opening 100 bottles, even if it would have been pleasant, I built a cork launcher. So you have the laser, the cork between, and the photodiode. I have a reference lens, but this is another story. The tube is connected to a gas bottle and I can open the valve to pop the cork. I will show you the result for two different frame rates. At 3800 frames per second, with the camera I have, the largest resolution I can get is 768/512 pixels. An image is recorded every 263 microseconds. The frame rate is too small to observe the gas dynamic and the video is not really fluent. Moreover, the image is wide saturated because the exposure time of the camera is too large. The exposure time is another parameter you can play with, and is the time the sensor is detecting the photons for each frame. Here the exposure time is too large, so some pixels are receiving too much photons, and the pixel intensity is at the maximum of 255 for an 8-bit image. With an 8-bit image, the intensity scale goes from 0 for fully black to 255 for fully white. Therefore, the color given to these pixels that are receiving too much photon is fully white, and we lose some information in some areas due to saturation. If you reduce the exposure time, you can increase the frame rate and avoid saturation. So setting the frame rate at 20,000 frames per second, I can get an image every 50 microseconds with a size of 512/128 pixels. You can see that the video is now fluent and you can observe the gas dynamic at the really beginning of the popping event. The exposure time was adjusted to avoid the saturation. These images are not recorded directly but indirectly with what is called a Schlieren optical system. Shortly, this system increases the perception of the density changes in the air. I invite you to go check a scientific paper we wrote about the dynamic of the cork popping event. This nice collaboration compares high-speed images to CFD simulations. I let you with the video of a real champagne bottle opening for which the camera was triggered with the laser. Don't forget to subscribe for more scientific contents. Subscribe. It's not a joke, subscribe.